Hello and welcome back to Abstract Linear Algebra, the video series where we generalize a lot of concepts from linear algebra. And indeed, in today's part 10, we will talk about general inner products and norms. These are notions that give more structure to the vector space besides the algebraic structure. However, before we start with the definitions, I first want to thank all the nice people who support the channel on Steady, here on YouTube or via Patreon. And please don't forget, with the link in the description, you find a lot of additional material for all the videos. Okay, then let's immediately start by considering an F vector space, and please recall, F always represents the real number line or the complex plane. Hence, the short notation to write this down is F is an element of this set. And now in order to keep the notation simple, we will use the same symbols in both cases. For example, for a scalar alpha, we will always use this bar to denote the complex conjugation. Therefore, for real numbers, the bar should not change anything. And that's exactly the definition we want to use here. So you see, this is just the formally correct way to extend our definition for the complex conjugation to the real case as well. It helps us in order to consider both cases at once. Moreover, the same thing we will do for matrices. So for any matrix A with m rows and n columns, we can define A star. Indeed, you should already know, in the complex case, this denotes our adjoint. This means we exchange the roles of rows and columns of the matrix and also use the complex conjugation in each entry. Therefore, if there is no complex conjugation, the only thing that remains is the transpose. In other words, if you see the star in the real case, we actually mean the transpose of the matrix A. Okay, with these notations cleared up, we can give the definition of a general inner product. Hence, this definition will generalize the standard inner product we already know from Rn and Cn. And indeed, we use the same common notation with the pointed brackets. So you see, we have a map with two inputs, so the domain of definition is the Cartesian product V times V. And as always, V stands for an F vector space. But the codomain of an inner product is always the field of scalars. And now this map here is called an inner product on V if it satisfies three properties. And indeed, I can tell you, they are not hard to remember at all. The thing you have to keep in mind for that is that with an inner product, we want to measure angles and lengths. And there please note, just the abstract vector space V does not have any geometry at all. It only has the algebraic structure, scaling and addition by definition. And that's the reason inner products are so helpful, because they give geometry to the vector space. Okay, but in order to get that, we need some reasonable properties. The first one is, if you put the same vector in both arguments of the inner product, it should measure a length. Therefore, the outcome has to be a non-negative real number. And indeed, no matter which point x from the vector space we put in. And please note here, even in the complex case, this here has to be a real number. And indeed, because we want to measure lengths, it should be a positive real number. Hence, the only case that the length can be 0 is for the 0 vector. So we also claim this implication, if the inner product like this is 0, we get that x is equal to 0. And as always, please note, here we have the real number 0, and here we have the 0 vector in V. Now, this is the first property of the inner product, and you can remember that as the inner product is positive definite. And indeed, it means both claims here together. Okay, then the second property is also not so hard. It says that the inner product should be a linear map in one of the entries. And there I can already tell you, I want that in the second argument. However, you also find mathematicians that do this definition in the first input. So please keep that in mind. There are two possibilities for the definition of an inner product, and there's no general agreement which one is better. But you should know, for all my videos, you see the definition with the second argument. Okay, but the property itself is not so hard, it's the linearity, so it means we can pull out the addition sign. And of course, this equality should hold no matter which vectors x, x tilde and y we choose in our vector space V. However, this is only one part of the linearity because we also want to pull out the scalar multiplication. This means this lambda here can be also written in front of the inner product. And in the same way, this should also hold for all possible inputs we have here. Okay, and now the second property you can remember by saying the inner product is linear in the second argument. Now this makes sense because it's definitely something the standard inner product also had. However, at least in Rn, the standard inner product is also linear in the first argument. So maybe we also want that, but it turns out that for the complex case, this is no longer true. More precisely, in the real case, the inner product should be symmetric, so it does not matter which is the first and the second argument. But this is not the case for complex vector spaces, because exchanging both vectors adds a complex conjugation. Indeed, we also know that from the standard inner product in Cn. In fact, we need this property such that it fits in with the first one, such that we can measure angles and lengths again. Okay, there we have it. These are all the properties for an inner product, and the last one we now simply call conjugate symmetric. Which simply means it's symmetric in the usual sense for a real vector space, but with a complex conjugation for a complex vector space. And now after all these discussions, I think we are ready for examples. And now the first one should be the already mentioned standard inner product. And here we can define it for the vector space Fn. And here you see, in order to make sure which inner product we have in front of us, I use the index standard here. And now you might recall, for the standard inner product, we just have to multiply the components and put a complex conjugation on the first one. And then we simply have to add all these combinations. So when you see this nice formula for the standard inner product in Fn, you might recall that we can also express it with a matrix product. In particular, if you see u and v as column vectors, then u star is a row vector. And if you multiply it with the column vector v as a matrix product, we get out a scalar. And now you should see the scalar result is exactly our inner product of u and v. Therefore, you can always remember the standard inner product with this definition as u star v. So it's a very nice formula and easy to use. And soon we will see that we can also generalize that to other vector spaces. But first, let's look at another example in F2. There we only have two components, so everything is a little bit simpler. And here we could say, in the definition, we mix up the components. So u1 is combined with v2 and u2 is combined with v1. Hence, we immediately see that the second and the third property are fulfilled. More concretely, the linearity and the conjugate symmetric property you can show as for the standard inner product. So this is not hard at all, and now the question is the first property also satisfied? For this we can first look at an example, so let's put in the same vector left and right. And let's keep it simple, let's choose 1 and -1 for the components. Okay, then two multiplications, not so hard, and we see we have -1, -1. Hence the result is -1, which is strictly less than 0. So we can immediately conclude that this definition does not give us a positive definite map. Hence this thing here is not an inner product for F2. So this is a counterexample. An inner product really has to fulfill all the three rules. Okay, and now for closing this video here, let's look at a positive example again. And here I want to take the polynomial space again, but with polynomials defined on the unit interval. And moreover, the codomain now should be given by f, so the complex numbers or the real numbers. So for example, we could have the polynomial p of x given as I times x. So this is a well-defined vector in our vector space, and please note, here it means that the variable x is still a real number between 0 and 1, but the coefficients could come from the complex numbers. And now it turns out that this vector space here can have a very nice inner product. This means we will be able to measure angles and lengths of polynomials. So maybe this sounds crazy first, but it implies that we have much more structure in the space. But I would say how to use this inner product we can discuss in more detail later. First, you should see here that the definition of this inner product is given by an integral. And since we only put in polynomials f and g, the only thing you have to integrate here are polynomials. So even with complex numbers involved, calculating these integrals should not be a problem. But maybe let's do that with the example from above, so let's put in p in both arguments. This means, by definition, inside the integral we have I times x, complex conjugated, times I times x again. So you should see, the integral we have to calculate here is x complex conjugated times x. However, I told you before, x is just a real number between 1 and 0, so we can just write x squared. And please note here, minus I squared is simply 1. Okay, now to solve this integral, we just need the antiderivative, which is 1 over 3 x to the power 3. And of course, we have to put in the limits, first 1 and then 0. And then we see the result is simply 1/3. So as expected for an inner product, we get out a real positive number. But only because we put in the same vector in both components. So if you put in two different vectors, the output can definitely be a negative number or a complex number. Okay, with this example you see that we can also have an inner product in an infinite dimensional vector space. So also in these cases, we are able to measure angles and lengths. And as I already told you, this is something we will do in more detail in later videos. And for the end of this video, I want to tell you that the appearance of the integral is not so strange. Maybe you recall the standard inner product from before was given by a sum ui times vi, where u gets a complex conjugation. And now you should see this whole sum gets transformed into an integral. But still we see the complex conjugation is on the first function here. Otherwise it looks very similar. It's a combination in this multiplication of all components, but for the infinite dimensional case we have infinitely many of them. So I would say this is one possibility to remember this formula here. Okay, I think that's good enough for today. In the next video we will look at more examples for inner products and so-called positive definite matrices. Therefore, I really hope we meet again and have a nice day. Bye bye.